Uh, so hello everybody. Today we would like to talk about modeling in the frequency domain, which is chapter 2 in our book. Um, so I would like to go to next slide. So in this chapter, in fact, there are some learning outcomes which we need to achieve. First, we need to find Laplace transform of time functions and the inverse Laplace transform. This is very important. So this is basic foundation. We need to know how to get Laplace transform of a time function and how can we get the inverse Laplace transform of a function in its domain to get its time response. Find the transfer function from differential equation and solve the differential equation using the transfer function. This is sometimes you have very complex differential equation, and one way for solving it is to convert it into its domain using Laplace transform, simplify it, and use inverse Laplace transform one more time to find the solution of your differential equation. Also find the transfer function for linear time invariant electrical network. We will do it in part 2 of this lecture. And also find the transfer function for linear time invariant translational mechanical system. Find the transfer function of rotational mechanical system. Find the transfer function for gear systems with loss and gear system with no loss. Find the transfer function for linear time invariant electromechanical system. And linearization also, we will try to linearize a nonlinear system in order to find the transfer function. Those nonlinear systems are very complex systems, and it's very important to linearize it around a certain operating point before controlling it, because it's complex. And there's a problem, most of the control system techniques which are developed over maybe 100 years, they are designed for linear systems. So if you want to use those techniques, you have to linearize your system. And when we linearize our system, in fact, we try to approximate it. We try to make assumptions that my system will stay around this operating point. So we have some assumption that my system will be working in this around this operating points, for example. So in this case, we can simplify it, we can linearize it, and we can design a controller using linear methods to be applied to this nonlinear system, assuming that it will stay around this operating point. If it will not be able to stay around this operating point, your system will not work. So first, what is frequency domain? Because we are starting in this unit by frequency domain and Laplace transform. So obtaining a mathematical representation of a system is important for control design and analysis. It's very important if I need to design a controller. In fact, it's very important to have a model of your system so I can design my controller, test my controller, and after that, I will apply it to my system. But it's impossible to design a controller and just attach it to your system and try to adjust the controller parameters by trial and error. It will not work. So it's important to start by a model of your system, modeling it. We need to model our system. We need to find a good representation of your system. We can obtain this model or this representation in the form of a transfer function, which we will do here in chapter 2, or it could be in the form of a state space representation, which we will study in chapter 3. So in chapter 2, we will deal with systems in frequency domain, and in chapter 3, we will deal with maybe the same system, but in the time domain. A system could be given in the form of a differential equation, which is in time domain. If the system is composed of cascaded blocks, it would be much easier to use transfer functions to simplify it by simple multiplications. So maybe your system is represented by a differential equation, and this differential equation is very complex. So it's very important to try to get the transfer function of your system and try to simplify your system into subsystems. So it will be easy to manage your system and control it. An over transfer function of a cascade system can be obtained by combining transfer functions of each individual block, which cannot be obtained using differential equation. As you can see here in this figure, you have a system. We look into B first. I mean, this system B is a system which consists of subsystems, right? So if you want to find the overall transfer function, the overall transfer function will be the output divided by the input, assuming zero initial conditions. This is the definition of transfer function. So in fact, in this case, we can just multiply those subsystems in order to get your system. If you want to go in the opposite direction from A to B, you have a system and you want to simplify it. So you have differential equation, you have C of t as a function. I mean, you have equation of C of t. In this case, you can just put it in S domain, and then when you put it in S domain, you can use maybe partial fraction expansion. So at the end, my system will be a summation or a multiplication of much simpler systems. So a system represented by differential equation is difficult to model as a block diagram. So it is desired to convert it into frequency domain using Laplace transform. If your system is given in time domain, it's difficult, in fact, to design controllers, because also those control system techniques which has been designed over years, they have been designed, in fact, for systems represented in S domain, because S domain was much easier before. I mean, if you can go back 1950, for example, or something, it was very difficult because at the time they don't have computational power, good computers to simulate systems in time domain. So it was much easier, in fact, to put systems in frequency domain and try to put the response in papers before digitalization, and try to design a controller to achieve those requirements in the frequency domain and not in the time domain. Time domain, on the other side, time domain, it's a time domain representation of control system, focus on how this system will respond over time to an input signal. So as you can see here, if we can draw it, you have a system which is a block diagram, and this system has some input, and you try to plot the output. So the output, it could be, for example, y of t or c of t, and the input would be r of t. And in this block here, we will have a transfer function or differential equation, which will represent the system dynamics. So it's a direct analysis of the physical signal in real time. The system has parameters in the time domain. You look at parameters such as maybe rise time, which is the time which your system will use to go from, okay, I want just fix. So for example, yes. So as you can see here, this is the response of my system, right? So this is my response. Starting from initial conditions, it will overshoot, undershoot, oscillate a little bit, and after that it will go to steady state. So we can say that, okay, this part, we call it steady state. That part, we call it transient response. So my response consists of two parts. One part, we call it transient response, and it will be followed by steady state. Our goal, in fact, is to reach this steady state. So there are some parameters which can be used to characterize your transient response. One of those parameters is the rise time. The rise time is the time which will be used by the system to increase its output from 10% to 90% of the output value, right? To the desired value. I know the desired value is 1. We need to reach this value, which is the desired value. So the rise time will be the time which the system will use to go from 10% to 90% of its final value, for example. So this is the definition of rise time. We can have also something called settling time, as you can see here. So in fact, the settling time, the definition of the settling time is a time which the system will use to go from 0 to 95%, in fact, to the final value plus minus 5%. So when you reach 95% of your final value, you can say that, okay, now you are in steady state. You are finishing transient response. So this is the definition of the settling time. So this is the time which the system will use to reach the final value plus minus 5%. So when you are reaching 95% of the final value, you can just say that, okay, now you are in the setting, in the steady state. You are finishing transient response and you are in the steady state. We have also overshoot. This overshoot, as you can see, also, this overshoot, I mean, if your amplification is a little bit higher, so you will not go slowly, in fact. So you can build up speed much higher, at much higher speed, and you will overshoot. So this overshoot, it's very, this is, we call it maximum overshoot. You can have maximum overshoot A, and you can have some multiple overshoots, in fact, in your system. And it will happen at a time called the Tmax. Those Tmax, it's the time at which we have the maximum overshoot. So one of the desired requirements, in fact, is to have Tmax. I mean, you need to get maximum overshoot of maybe 20% or 15% at a specific point of time at Tmax. So those are design requirements which we might need to achieve. This overshoot, it's not required in many applications, but in some certain applications, it's important for us. So we have also steady state error, for example. So when you go to steady state, we will have here only one coefficient. We call it steady state error. So in some applications, we need to have steady state error equal 0. So similar to the example of the elevator, I cannot have an elevator with steady state error equal 30 centimeters or plus minus 30 centimeters, because in this case, you will not be able to level in your destination floor. You will be below or above it by maybe 30 centimeters. It's not acceptable. So in many applications, it's very, very important to have a steady state error equal 0. So in the analysis, you often use differential equations to describe the system dynamics. In time domain analysis, try to address the behavior of your system with respect to time. So as you can see here, we are plotting the response of your system against time, which is easy for us to understand. Such as response to, we can get this response, we call this response, in fact, step response. So this one, we call it unit step response of a control system. Why unit step? Because the desired input is 1, right? When it could be step input, or it could be unit step input. When it is unit step input, it means the input is 1. So we need to reach 1, and the response of the system will start increasing from 0. This is my initial conditions. It's very similar to driving your car early morning, for example. You just drive your car. It was parked in your car at your home, for example. So it will go from location 0 or speed 0 until it reaches a final speed. So we call this one, it's a step response. And in fact, step response is very important because it's a harsh, in fact. Do you see? It's a step response. You go from 0 to 1 immediately. So it's a very hard test. So step response, it's very important in control system because it's tough test. Because you need to test your system when the desired input goes from 0 to 1 immediately, right? So there is no transition. I mean, I try to test my system with the toughest input or desired input, for example. So your desired input, it will go from 0. So imagine that before t equals 0, when time is negative here, so the desired input was 0, right? So it was 0, and after that it will go from 0 to 1 immediately. And after that, we need to follow this signal. So step signal, in fact, it's very important because it's a very tough signal which is used for testing your system. When you are testing your system, I need to test it with something tough, not something easy, for example, because I need to see the performance of your system. So we use this unit step response to test the system dynamics, the system behavior, to ensure that your system will be able to achieve your design requirements. Usefulness. Time domain is useful for understanding the transient and steady state response of your system. But just remember that the transient response, we call it natural component or the natural response. A steady state response, we call it forced response. And this forced response, it's due to the input. It's not due to your system dynamics. It's due to the input. But the transient response, it's due to the system dynamics. The response due to the system dynamics, which is a natural component, it should decay over time. We need this part to decay. So after settling time, we don't want to see any dynamics, any system dynamics, because we will reach a steady state and we need to stay in this steady state. So, okay, so we can... So in frequency, in fact, in frequency domain, so the definition, what is the definition? Oh, I need to remove those annotations. Sorry for. Should be able to clean or yes. So frequency domain, what is the definition of the frequency domain? Frequency domain representation of a control system analysis. It helps us to see how the system behaves in response to a sinusoidal input. So instead of having step input in time domain, in the frequency domain, we need to see the response of your system for a sinusoidal input, for a sine function of different frequencies. And it essentially looks at how the system process different frequencies within an input signal. So we try to check the system response in the frequency domain against sinusoidal input. parameters which are used here in the frequency domain, we try to look into gain margin, phase margin, bandwidth, and resonant peak. We use tools also for the analysis. We use tools like Bode plot, Nyquist plot, and the frequency response of the system to understand how the system behaves at different frequencies. So as you can see here in this figure, we call it frequency plot. So we try to check the system behavior against different frequencies. So the analysis involves transforming time domain differential equation into frequency domain. If I need to check the system response in frequency domain, I need to convert my differential equation into a transfer function. So if you want to work in frequency domain, I need to put the system in a format which will help me to check its behavior in frequency domain, which is a transfer function. But if you want to work in time domain, I need to convert my transfer function again into steady space representation. So in fact, in chapter 2, we will work with transfer function, and in chapter 3, we will work with steady space representation. Both are the same, in fact. It's just we try to look into the system from different perspectives. If you try to look into the system in frequency domain, I need to use representation, which will help me to check the system response in frequency domain, which is the transfer function. If you want to check your performance in time domain, in this case, I need to have maybe a differential equation or a steady space representation. Usually, it's a steady space representation, not a differential equation. We need to convert it again into frequency domain using Laplace transform. So Laplace transform, this is a magical tool which will help us to jump from frequency domain into time domain and back again into frequency domain. So I can use Laplace transform to convert my system from time domain into frequency domain. You will do your analysis, you will design your controller in the frequency domain, and after that you will go back into time domain using inverse Laplace transform. So Laplace transform convert you from T to S, and inverse Laplace transform, it will convert you back from S to T. Frequency domain is powerful for understanding system stability and the design of controllers, especially for complex systems where time domain analysis can be challenging. Sometimes your system is too complex, and the analysis on the time domain, it will be very challenging due to computational power, other challenges, for example. But you can simplify this and you can do this quickly, in fact, in the frequency domain. When you look into the characteristic polynomial of your the roots of your characteristic polynomials of your transfer function, you can find the locations quickly of your poles, for example. And in this case, you will be able to say that, okay, my system is stable or is unstable. Okay, so time domain versus frequency domain. Time domain is useful for understanding how a system responds to different inputs over time, focusing on the actual time response of the system. We understand time response. It's easy for us because we are living in time domain. We are not living in frequency domain. But also frequency domain, on the other hand, is useful for understanding how a system behaves across different frequencies, which is very important. And therefore, because those frequencies, it could change from time to time. So it's important to check the system performance against different range of frequencies. And it's important for the stability analysis and the controller design. I need to ensure that my system will be stable at different frequencies. For example, sometimes they design a bridge, for example, and this bridge, it's stable, but when we get some maybe earthquake or maybe wind, for example, it will start, moving, for example, and then when it reaches a certain frequency, it will be damaged, right? So they need to design it to sustain those different vibrations, for example. So control system designers often use both domains to get a complete understanding of system behavior and to design appropriate controllers. And this is what we will do in this course. We will try to use frequency domain and the time domain to understand the system in a better way and to try to design good controllers which can control the system over different operating conditions or frequencies. In that part, we will start with the Laplace transform and its inverse. So we have Laplace transform and we have inverse Laplace transform. We have this equation, and this equation, it is used to convert a function from time domain into frequency domain. So you have a function which is f of t. It could be a differential equation or a signal, and we need to convert it into its frequency equivalence, which will be f of s. So in fact, we just replace T with S. T, it's time domain. S, it's frequency domain. It's complex. So Laplace transform is mathematical technique which is used to transform a function of time, such as a signal or a system response, into a function of complex frequency f of s. It is a typical integral transform that is particularly powerful for solving linear ordinary differential equation that arise in system analysis, control engineering, and many other areas of applied mathematics. So usually, if you have a complex differential equation and you cannot solve it, it will be easy to just convert it into S domain and solve it, right? So Laplace transform of a function f of t is defined for all real numbers for t greater than or equal 0. It will be the function f of s, which will be defined using this integration. So to integration from 0 to infinity, exponential minus st multiplied by this function dt. In fact, any function, you can just do it. You can, if you have any function f of t, you can just do this transformation. For example, if f of t is at, for example, so now I can just do this integration and try to solve it and find its equivalence in the frequency domain, which will be 1 divided by s minus a, right? So s is complex number, which is it's a delta plus g omega. So it's a real part plus imaginary part, with the real part and imaginary part sigma and omega. So we got the system response to a sinusoidal input with frequency omega, whose amplitude increases or decreases exponentially by sigma. E is the base of natural algorithm, and T represents the time. So this is the equation which we can use. But in fact, we are lucky because we don't need to do this integration. We have a table. We can use this table for solving those Laplace transform stuff. So this is the equation of Laplace transform, and this is the inverse Laplace transform. So in Laplace transform, we are starting with a function in time domain, and we try to get f of s. So it will be the integration from 0 to infinity. This function multiplied by exponential minus st dt. If you need to do inverse Laplace transform, we need to do the opposite. So inverse Laplace transform of f of s, it will be this integration of f of s, because I need to convert f of s into f of t, right? So we have in Laplace transform and inverse Laplace transform. In fact, we don't need, in fact, to do this because we can just use this table. And as you can see here in this table, in the left-hand side, we have this function of t, those functions in time domain, and in the right-hand side, we have f of s. So if you have a function which is step function 1, right? So f of t equal 1 means it's a step input. In fact, it's this one, right? It's a signal also, but it's a step input. If you want to convert it into S domain, it would be 1 divided by S. If you have this function, which is exponential at, it will be converted to 1 divided by S minus e. If you have t to the power of n, I mean, if n equal 1, it would be ramp signal. It would be something like this one, correct? So if you have this function, it will be factorial of n divided by s to the power of n plus 1. So if this function is t, just t, because usually we have many t's. So if it is t, so it will be 1 divided by s squared, because t has a power of n equal 1. We just, I mean, the factorial of 1 is 1 divided by s to the power of 1 plus 1. So it will be 1 divided by s squared. Sine at, cosine at, hyperbolic sine, cosine, and so on. So we have this table, and we need to use this table for solving our problems. So if you need to apply Laplace transform or inverse Laplace transform, you need to start Laplace transform. We need to start from f of t and try to get f of s. If you need to do inverse Laplace transform, so in this case, we need to go in the opposite direction. We need to start with f of s, try to put our function in a form similar to those in the table, and try to get f of t from it. So we will use a table for solving Laplace and inverse Laplace transform. Yes. So the advantage of Laplace transform, Laplace transform has the ability to convert differential equations, which can be difficult to solve, into algebraic equation, which are much easier to handle. So, I mean, sometimes you have very complex functions, and it's difficult to solve differential equations. So it would be easy to just convert it into S domain, and when it is in S domain, it will be algebraic equation. So just summation of items, components, or multiplications. So it will be easy to simplify and solve. In the context of control system, Laplace transform is used to convert system equations from the time domain into frequency domain, where the behavior of your system can be analyzed using algebraic methods. This is particularly useful for understanding the stability and frequency response of a system and for designing appropriate feedback control system. So, in fact, if your system is in time domain and it's complex, just get the transfer function, check your stability of your system, design controller, check the stability of your overall control system, and go ahead using your system in frequency domain. By applying the inverse Laplace transform, one can convert frequency domain function back into time domain, which can help you to predict the system behavior in real-time scenarios. So sometimes my system is in frequency domain, but I need to check it in time domain. So one easy way for doing this is to get the overall transfer function of your system. So for example, I can plot here, if your system is like this one, the G of S, you have a controller, you have a feedback closed loop system. So all what we need, in fact, is to get the overall transfer function of your system, convert this one into time domain, right? And when it is in time domain, I can just simulate my system and deploy the response to see that you are able to achieve your design requirements. Because maybe I need to achieve some, and my design requirements will be in time domain. I need to have this maximum overshoot, Tmax, and so on. So in this case, I will design my system in frequency domain, but I will not be able to see those numbers. If you want to see that your controller is able to achieve the design requirements, it's very important to get the overall transfer function of your control system, which will be T of S, not G of S, because G of S, it is the open loop transfer function of your system. We need to get the closed loop transfer function of your system, convert this one in time domain, and just write very simple code to plot the response of your system. So this is the Laplace transform theory and the equations which can be used. You have it in the book in many sources. So now we need to start with an example. You have this differential equation and we need to solve it. So it's f double dash of t plus 3f dash of t plus 2f t equals 0. And we have some initial conditions. My initial conditions are f of 0 equal 1 and f dash of 0 equal 0. We need to solve this one. So we will take the Laplace transform of this side equal to the Laplace transform of the other side. So Laplace transform of that part equal 0, because Laplace transform of 0 is 0. So we will take Laplace transform of the first term, f double dash. F double dash, it is the second derivative of the function. So it will be s squared f of s minus s multiplied by f0 minus f dash 0. So this part will be the first term. The second term, it's a 3f dash of t. So it will be, this is the first derivative of equation. So it will be 3s f of s minus f of 0. So this is my initial condition. And the third term will be 2 multiplied by f of t. So it will be 2 multiplied by f capital of s. So now we did this Laplace transform. So just to try to simplify it, we know that f0 equal 1. So this one will be 1 multiplied by s. This one will be 0. This one will be 1, correct? So just to try to simplify it, so it will be s squared f of s minus s plus 3s f of s minus 1 minus 1 multiplied by 3, so it will be minus 3 plus 2f of s. Take f of s as a common factor. So we have here s squared plus 3s plus 2. So we will have this term. We have here minus s minus 3. Just to transfer that part to the other side, move it to the other side. So at the end, my equation will be like this one. It will be s squared plus 3s plus 2 multiplied by f of s equal s plus 3. We will move it to the right-hand side. So it will be like this one. Now I need to get f of s. So just to divide both sides by that part. So at the end, we will have f of s equal s plus 3 divided by s squared plus 3s plus 2. So this is very nice. So now we are converting our differential equation from this form into this form. But we need to solve this differential equation, which means we need to get f of t. right? We need to get f of t. Of course, you can look into this differential equation, f of t equal minus f double dash minus 3f dash divided by 2. No, but this is, how can we get f dash and f double dash, right? So now we simplified this differential equation, and we have it in S domain like this one. If you want to solve this one, we need to convert this one into, it's algebraic equation, in fact. So we just need to simplify it more, right? So we need to have it as a summation of maybe more first order coefficients or factors, because we need to use the table, in fact, for getting the solution. So this one, we will try to simplify it more. So we can see, we can look into the part here. So it's s squared plus 3s plus 2. Maybe we can factorize it. So it will be s plus 1 multiplied by s plus 2, right? So if you want to be sure that you did it correctly, just do multiply s by s. So it will be s squared. We have here 1s plus 2s. It will be 3s. And 1 times 2 equal to that part. So now it's okay. And we have here s plus 3. So now my f of s is s plus 3 divided by s plus 1 multiplied by s plus 2. Can just use something called the partial fraction expansion. So it will be like a divided by s plus 1 plus b divided by s plus 2. And now we need to get the value of a and b. What will be the value of a? You will take the limit of this term. I mean, a will be the s plus 1 multiplied by this term as s goes to minus 1. So it will be minus 1 plus 3, which is 2, divided by minus 1 plus 2, which is 1. So it will be 2 divided by s plus 1. We will look into the other one, s plus 2 term, multiply both sides by s plus 2, take the limit as s go to minus 2. So it will be minus 2 plus 3, it will be 1. Minus 2 plus 1, it will be minus 1. So it will be minus 1, right? So this one will be minus 1. So now we have our equation f of s as a summation of two simple terms, right? So now it's easy. We can go into the table, Laplace transform the table, and from this one, we can try to find f of t. So in this case, f of t will be 2 exponential minus t minus this one, 1 multiplied by exponential minus t. So now we can solve it in time domain, right? Now we solved our differential equation, and we can get f of t. So this is how we solve it. And as you can see, this is exponential, negative exponential, negative exponential. So as t goes to infinity, that part will go to 0, in fact. So if you can substitute t here equal infinity, so in fact, f of t will be 0. Because 2 exponential minus infinity, it would be 0 minus 0. So this one will be 0. So if you want to plot the response of that part, it will be something starting from some initial conditions. You can put t equal at t equals 0. This one will be 2 times 1 minus 1. It was starting from 1 here, and it will go down like this one, and it will disappear. So the response will be like this one, right? So if you want to see the response, because this function, it's just function of time. We don't have any forced component here. We don't have any constant value. So the response of this part, it will look like this one. You just put t, substitute t equals 0, so it will be 1. And when t go to infinity, it will go to 0. So the response will be something similar to this one. So this is how we can solve a differential equation using Laplace transform. We need to have another example. Of course, you can go to Python code and try to simulate it in Python. So in example 2, we have this equation. But this equation, it's in time domain, and we need to solve it using the formula. We need to use the formula for solving it. Yeah, we will go to the formula. So the formula is f of s equal integration from 0 to infinity, f of t exponential minus st dt. Substitute f of t, so it will be a multiplied by exponential minus at multiplied by e exponential minus st. A, it's constant, so take this constant outside the integration. So a multiplied by the integration from 0 to infinity, exponential minus s plus a t dt. Just integrate, so the integration of the exponential part, it will be the same exponential part divided by the first derivative of the power. So the first derivative of the power, it will be negative 1 divided by s plus a. So it will be minus a divided by s plus a multiplied by this exponential term and substitute by t from 0 to infinity because this is integration from 0 to infinity. So substitute the upper bound first. So we will set t equal infinity minus exponential 0. So it will be exponential minus infinity minus exponential 0. Exponential minus infinity, it's like 1 divided by exponential infinity, and the exponential infinity is infinity. So it will be 1 divided by infinity, it will be 0, and exponential 0, it will be 1. So this one will be minus 1. Minus 1 multiplied by minus a divided by sa, so it will be a divided by sa. So in this case, in fact, we can get this one from the table, but now we can say that if you have a function which is e exponential minus at, f of s will be 1 divided by s minus a. So it will be 1 divided by s plus a, right? So we can get it from the table, or we can get it from the formula. Okay, we can go to the third example. So in this example, find the inverse Laplace transform of the following forms, right? We have this, try to find the inverse Laplace transform of this one. So we will start with this first one here, right? This is f of s, 6 divided by s. So we need to get f of t. So what will be f of t? 6 divided by s. It's constant. Remember, when we have from the table, when it is 1, it will be 1 divided by s. So this one will be just 6 minus 1 divided by s minus 8. So it will be, we have this minus here, remember? It will be exponential minus at, right? Exponential minus at, so it will be exponential minus 8. So it will be plus 8t plus 4 exponential minus 3, it will be 3t. So it will be like this one. And when you look into this equation here, in fact, right? When you look into this equation, you see that, okay, this is the forced component. This is the natural component. This is forced. This is natural. This natural, it's a transient response. And this forced component, this is a steady state. But just remember that here we have one problem here because exponentials are positives. When this one is positive, it means that part will grow unbounded. It will go to infinity, in fact, when time goes to infinity. So in fact, this system, if f of s is representing a system, this system is unstable, right? Okay, we go to the second one. So this function, yeah, we did it already. Okay, so this is the solution, in fact. So we got 6 minus exponential at plus 4 exponential, oh, we forgot here 4, just remember. 4 multiplied by exponential 3t. So this is a transient response, and this one is the steady state response. Okay, we have here another example. H of s equal 19 divided by s plus 2 minus, okay, this one. So let us solve this one. So now h of t, we need to convert it into time domain. So h small of t equal this one. It would be 19 exponential minus 2 t. Very good. This one also we need to fix it a little bit. I mean, before solving this one, in the table we have only s. So in fact, we need to divide here by 3. So this one we need to make it like, we need to take s as a common factor. So it should be like 3 multiplied by s minus 5 divided by 3. We need to have it like this one. So this one should be 1 divided by 3 negative multiplied by 1 divided by s minus 5 divided by 3. It will be like this one. So in this case, it will be minus 1 divided by 3 exponential minus 5 divided by 3. So it will be plus 5 divided by 3 multiplied by t. Wow. Correct? So now we have that part. What about that part here? 7 divided by 1 divided by s to the power of 5. So it will be plus 7 multiplied by t. Remember? Do you remember this equation? When it is 2 to the power of n, it will be factorial of n divided by s to the power of n plus 1. Just here, both here, okay. So just here in that part, 7 divided by s to the power of 5. So we can say that, okay, n plus 1 equal 5. So n equal 4, because I need to put it in that format in order to convert it into time domain. So when n equal 4, so we should expect that we should have factorial of 4 divided by s to the power of 4 plus 1, right? If it is like this one should be converted into t to the power of 4, right? So anyway, we will have here t to the power of 4, but we need to calculate the coefficient, right? We need to have here 4, factorial 4. Factorial 4, in fact, factorial 4 equal 4 multiplied by 3 multiplied by 2 multiplied by 1. So it will be 4 times 3, it's 12, multiplied by 2, it will be 24. So we need to multiply this one by 24. If you want to multiply this one by 24, we multiplied it already by 24. We need to divide by 24, right? So we just need to fix it like this one. So now it will be like this one. It will be 19 exponential minus 2t minus 1/3 multiplied by exponential 5 divided by 3t plus 7 divided by 24 multiplied by t to the power of 4. Now we have our function in time domain. When you look into it, we don't have here any forced component, but we have only natural component. And the exponential part here, this one is okay. It's a ramp function. This is function, it's okay. But we have a bad component here. This component is very bad. This one is okay, because here it's exponential negative. It will decay with time. But we have here exponential plus. When it is exponential plus, it means it's unbounded. So in fact, if h of s is representing a system, this system will not be stable, right? And also it's not linear, in fact. When you have power higher than 1, right? We have here 2 to the power of 4, right? So your system will not be a linear system. So in this case, we can go to the next example, and if you want, you can just play back those sections one more time if you would like to. So now we will go to example number 4, and the example number 4 here, we need to find inverse Laplace transform of this function. F of s equal 2 divided by s plus 1 multiplied by s plus 2. So in fact, we try to convert it into a simpler form. So it's a second order because here we have s squared. So using this approach, we will convert it into a summation of first order. This one second order. This one second order. When we do this partial fraction expansion, we will convert it into a sum of simpler terms. Sum of two first order systems. Because this one is easy, in fact. I mean, if we can get this one, it's easy. Just, I mean, it will be k1 multiplied by exponential minus t plus k2 exponential minus 2t, right? So it's easy. When we do it like this one, it will be easy. And now we just need to find the value of k1 and the k2. How can we find the k1? Just multiply f of s by that part, and it takes the limit as s go to minus 1. So as s go to minus 1, so it will be 2 divided by minus 1 plus 2, so it will be 2. So in fact, this one will be 2 e minus t. Okay? Yes, so now we need to get k2. If you want to get k2, you need to multiply f of s by s plus 2, right? Okay. You need to multiply f of s by s plus 2. When we multiply that part by s plus 2 will disappear. And it takes the limit as s go to minus 2. So it would be 2 divided by minus 2 plus 1, which is minus 1. So it will be 2 divided by minus 1, it will be minus 2. So this one will be minus 2 exponential minus 2t, right? So now we can solve it quickly, right? We can solve it very quickly. So we use partial fraction expansion because partial fraction expansion, it will help us to convert my complex function into a summation of more simpler terms. And as you can see here, this exponential negative, which means this term will decay with time. If we need to plot it, it will be like this one over t. And when t equals 0, just put t equals 0, so it will be 2 multiplied by exponential 0 minus 2, so it will be 0, in fact, it will be 0, right? And when t go to infinity, it will be just 0, so maybe it will be something like this one, right? So it will decay because this is natural component, and in this equation we don't have any forced component because we don't have any inputs, right? Okay, so we can go to the next. So the solution will be something like this one, right? So it will be yes. Okay, so we will go to the next example, which is example number 5. We need to find the Laplace transform solution of a differential equation. We have a differential equation, and we need to find the Laplace transform. Laplace transform solution of a differential equation. Find y of t if all initial conditions are zeros. Thank you very much. He make it easy for us. We need to find y of t from this equation. I will write this equation in a different format, right? Maybe similar to the example which we solved it. So it will be like y double dash plus 12 y dash plus 32y equal 32u. Now we need to apply Laplace transform. So y double dash, it will be s square y of s plus 12 s multiplied by y of s. This one I will make it s plus 32 y of s. So I will just take y of s as a common factor equal this one. It will be 32 multiplied by u of s because I don't know what is the value of u of t, right? So Laplace transform of u of t, it's u of s. But I don't know. I mean, he should tell me, in fact, right? He should tell me what is the value of u of t. I don't know. Is it step? Is it 1? Correct? If it is 1, it will be 1 divided by s. Yes. So anyway, we will get, if you want to get the transfer function, so it will be g of s equal y of s divided by u of s. So it will be, so look, u of s divided by y of u of s, it will be the coefficient of u of s. You will go opposite in that direction, right? If you will go in that direction, I need to get y of s divided by u of s. So it will equal 32 divided by that part. So it will be 32 divided by s squared plus 12s plus 32. If you want to make it beautiful, just put it in a block diagram. So it would be, my block diagram would be something like this one. Your input is u of s. Your output will be y of s. Your transfer function will be 32 divided by s squared plus 12s plus 32. It will be like this one. I don't know if you want to get y of s or y of t, for example, we need to see, I mean, for what input. So if we will say, okay, u of t equal 1. So in this case, in fact, u of s will be 1 divided by s. And in this case, we can say that, okay, so y of s will be, just multiply this one by y divided by s. So it will be 32 divided by s multiplied by s squared plus 12s plus 32. So it will be like this one. For step input, we assuming that u of t equal 1, which is a step input, because as I told you, unit step response is very important. Unit step response. So I have a system, and I need to check the response of your system against unit step. So this is my unit step. So this one will be u of t equal 1. So u of s will be 1 divided by s, and I need to plot the response of your system against time. So in this case, your output will be 32 divided by this one. If you want to use Laplace transform, we need to, because this is complex, it's s multiplied by s squared. If you look into the table, it's difficult, in fact. So we need to factorize it. So we need to look into s squared plus 12s plus 32. I mean, 32, it could be 4 times 8. So in fact, this term, we can factorize it into this one. It should be s plus 4 multiplied by s plus 8. If you are not sure, go back again. So it will be s multiplied by s. It will be s squared. 4 times s plus 8 times s, it will be 12s. And the 4 times 8, it's 32. So this is correct. So now it's 32 divided by 3 terms. So we need to convert it into a summation of more simpler terms. So it will be K1 divided by S plus K2 divided by S plus 4 plus K3 divided by S plus 8, right? If you want to get it in time domain now, it's easy, but I need to get K1. What is the value of K1? Just hide this S and substitute S equal 0 into this part. So it will be 32 divided by 4 multiplied by 8. 4 multiplied by 8 is 32. So in fact, the K1 will be 1. K2, if we need to get K2, so in this case, okay, just clean, right? So in this case, in this case, multiply both sides by S plus 4. So S plus 4 will disappear. And substitute S equal minus 4. So it will be 32 divided by this one will be minus 4. This one will be minus 4 plus 8. Minus 4 plus 8, it's 4. 4 times 4, it's 16, negative 16, in fact. So it will be 32 divided by negative 16. So it will be negative. This one will be minus 2. If you want to get K3, how can we get K3? So it's the same. Just clean first, right? If I want to get K3, so I will multiply both sides by this term, which is S plus 8, and it takes the limit as S equal minus 8. So that part will disappear because we will multiply both sides by S plus 8, and we will substitute S equal minus 8. So this one will be minus 8. This one will be minus 8. Minus 8 plus 4, it's minus 4. Minus 4 times minus 8, it would be plus 32. So K2, in fact, it will be 32 divided by 32. So this one will be 1. So in fact, now if you want to get y of t, so y of t will equal y of t equal. It will be this 1 divided by s inverse Laplace transform of 1 divided by s. It will be 1. K2, it's minus 2. So it will be minus 2 exponential minus 4t plus exponential minus 80. So now we solve it. Now we can get an equation for y of t. And just remember, look into the forced component. So this response, it consists of constant term. We call this one, it's the forced component. This forced component, it's due to the input, And as you can see here, it's just 1 because we selected the input here equal 1. And the rest will be natural response, this natural response. This natural response, it will make the transient response. And that part, it will decay over time because it's exponential negative and exponential negative. So it will decay over time. So when time goes to infinity, this part will be 0, and what will remain will be only 1. And in this case, if you look into this graph, if we need to plot the response of your system, the response of your system will be something like this one. Correct? So we will have here transient response. It will decay after some time, and what will remain here will be steady state response. And steady state error will be 0, in fact. ESS equal 0. Why is ESS equal 0? Because as you can see here, the forced component equal 1. It's not 0.9. If it is 0.9, we can say that ESS will be 0.1. So, but ESS here, the forced component is 1, and the input is 1. So, at steady state, we will be able to reach this desired input. Okay, so now we will go to the next example. Okay, now we solved this example. Now we can get the same results. And we can also use Python to plot it. If you want to use Python for plotting it, it should be easy. You just need to generate t, correct? And after that, write your function here and just plot it. And as you can see here, the response will consist of one part. We call it transient response. And the other part will be steady state. And as you can see here, steady state equals 0. Okay, and also if you want, in fact, to plot maybe if you want to plot maybe different components, different elements of the equation, you can just divide it and try to plot each part. And as you can see, all those The exponential minus 40, it goes to 0. This exponential minus 40, it will go to 0, correct? It will disappear. And also exponential minus 8, it also will disappear, which means those are natural components, which will decay over time. So now we will go to the example, to the next example, which is example number 6. And in this example number 6, we have more complex function to where we need to find inverse Laplace transform. I mean, you can see here the order 3 and the order here is 2. When the order here is higher than the order here, we need to use long division. And in this long division, we will divide that part by that part. So we will start, it will be like this one. So we will divide s cubed by s squared. So it will be s, we will have here s. Multiply s by that part. So it will be s cubed plus s squared plus 5s. Change the sign and take summation. So this part will cancel that part. So it will be 2s squared minus s squared. It will be s squared. 6s minus 5s, it will be s plus 7. This one, it's still higher, so we can make more division. So we will divide s squared by s squared. It would be plus 1. Do multiplication one more time. So it will be s squared plus s plus 5. Change the sign and take summation. This part will cancel each other. So we will have here 7 minus 5. It will be 2. So in this case, we can say that f of s equal s plus 1 plus the remainder. So it will be s plus 1 plus 2 divided by s squared plus s plus 5. You need to put this one in a form which is closer to the table, in fact. So it's s squared plus s plus 5. So you can just say that this one will be s squared plus s plus 1 divided by 4. So it will be s plus 1 divided by 2 squared minus, because you added here 1 divided by 4, I need to subtract 1 divided by 4. So minus 1 divided by 4 minus 5, it will be 19 divided by 4. And you can look into the table and try to find a formula which is closer to it, so you can solve it. So when you look into the table, I can find that we have this Laplace transform of omega divided by s minus alpha squared plus omega squared. It will be exponential alpha t multiplied by sine omega t. So we just try to find it in a form which is closer to this one. So here we have s plus 2 squared. So you can say that, okay, from that part, in fact, we can say that alpha equal minus 1 divided by 2, right? And we have here 19 divided by 4. I need to make it omega squared. So it's similar. It's 19 divided by 4. So we can say that it's square root of 19 divided by 4 squared. So we can say that, okay, now omega equal square root 19 divided by 4. So I need to have here 19 divided by 4, the square root, 19 divided by 4. If you will add it here, I need to divide by here. So I will add here 19 divided by 4, and I will multiply here by 4 divided by 19, which is the opposite. So this one times this one, in fact, it's 1. And we have here 2, which is coming from that part, the remainder. So it will be 2 multiplied by a square root of 4, it's 2. So in fact, it will be 2 times 2, it will be 4 divided by square root of 19. This one will be exponential minus alpha. Alpha equal minus 1 divided by 2. So it will be exponential minus, it's exponential alpha, as you can see here, exponential minus alpha t, minus alpha, right? So it will be exponential minus that part. So it will be exponential minus half t sine omega t, and omega equal square root 19 divided by 4. So now you have the function. So okay, so maybe we can do example number 6 and close that part, because now it's around 1 hour. Or maybe we can just leave this example number 6 for the next part. So thank you very much for listening.